Section 5.2 is on defining stoichiometry. Really what we're about to do is take all the concepts we've talked about this entire semester so far and roll them into one thing that we are going to call stoichiometry, or stoic for short. We're going to be utilizing the concept of getting mass into moles here in the next section. We're going to be utilizing balancing equations, figuring out what those actually mean, and kind of wrapping it all together into one thing to make sense of everything we've done so far this semester. So, section 1 dealt with balancing equations. So what does it actually tell you? Well, it tells you the relative amounts of each substance during a reaction. Okay, so this is going to be in, oops, switch over to the pen there. This is in moles, okay? Oops, in moles. The coefficients represent the mole ratios present in the reaction. So not by mass, but by moles. So in our balanced reaction here, 2Fe plus 3F2 yields 2FeF3. What that's saying is for every 2 moles of iron, you can make 2 moles of FeF3. So basically it comes out in a 1-to-1 ratio. However many moles of this you put into the reaction, you get that many moles out of it. Okay? And for every 3 moles of F2 you put into the reaction, you can make 2 moles of FeF3. So this one makes fewer moles in terms of from products to reactants. But these coefficients, the 2, the 3, and the 2, what do they really tell you? They are mole ratios. It's how much in moles you either need to make the reaction happen or how many you're going to produce based on where they are in the reaction. These ratios can be used to determine the relative amounts of substances, which is what we're going to be looking at this section, next section, and really for much the rest of the year. Okay, so stoichiometry as a definition: the study of the quantitative relationships between the amounts of reactants used and amounts of products formed by a chemical reaction. So how much stuff do you use up in moles based on the coefficients in the balanced equation, and how much stuff can you produce based on those same numbers? It's based on the law of conservation of mass. However much we start with is how much we've got to end with, right? You guys remember that from earlier this semester. The mass we start with has to equal the mass we end with. That's the conservation of mass. Okay, so here's another example. 4 iron plus 3 oxygen, O2, yields 2 Fe2O3. That's what's happening over here in the picture. Okay, it's how a lot of fireworks are made using these sorts of metals. For every 4 moles of iron used in the reaction, 2 moles of Fe2O3 are produced. So you get 1/2 the number of moles. Well, why isn't it 2-to-1? Well, it's because this 3 here makes this the simplest ratio, 4-to-3-to-2. But essentially, for every 2 moles of this you put in, you'd get 1, right? Or 4-to-2, however you want to write it here, 4-to-2. But we're going to use 4-to-2 in this instance because we want it in the smallest ratio, okay, whole number ratio. In the same sense there, then 8 moles of this would produce 4 moles of this. You'd get half as much this as product. Okay, that's really easy when the numbers are super nice to work with. Like if you plug in a 4 here, then that means you're only going to get 2. If you plug in an 8 here, you're only going to get 4. If you plugged in a 2 here, you're only going to get 1. When we start dealing with other numbers, okay, numbers with decimals, or when we have to start with grams, okay, because remember these are mole ratios, not gram ratios. We have to first get stuff into moles, convert, and then put it back into grams, which we'll see in the next section. A ratio between the number of moles of any 2 substances in a balanced chemical equation, we call those the mole ratios. Okay, so just kind of what we've been saying here. We're looking at the numbers. Just underline them to make sure we know what we're talking about. The 2, if there's nothing there, right, we assume it's a 1. So what we're talking about are those numbers up front, and it tells you how much of one thing you need to either make the other thing or react with the other thing. Okay, so our example here, 2 potassium plus 1 Br2 yields 2 kBr. For every 2 moles of potassium, 1 mole of Br2 is needed. Or, okay, so this goes all the way back to stuff we did in the first unit. We write conversion factors, yeah? Okay, a ratio of equivalent amounts. Okay, for every 2 moles of K, you need 1 mole of Br2 to react, or for every 1 mole of Br2, you need 2 moles of K. That's the ratio they react in. Okay, they are equivalent amounts, right? They are conversion factors. We could look at it this way. For every 2 moles of K, 2 moles of KBr is produced. So 2 moles of K is going to give us 2 moles of KBr. We're not going to simplify it. We're going to write the numbers as 2 over 2 to make sure that we're not skipping anything, right? We could write that flipped, okay, just like we did with conversion factors back in Unit 1, right? Since they're equivalent values, you could write it on either side, okay, of that division bar. Right, and then just one more here. We could have 1 mole of Br2 for every 2 moles of KBr, or 2 moles of KBr for every 1 mole of Br2, right? We can flip it, okay, because those are equivalent values. All right, so what we are going to do here is balance this and then write out our possible, okay, conversion factors or mole ratios. So we are balancing this. Okay, we got sodium over here, hydrogen, and oxygen. I'll write everything in the same order. So this is a 1, 2, 1. This is going to be 1. This is going to be 3, and that's going to be 1. So we are going to need to start with the hydrogen here. Looks like we don't have any other options. This may not be the easiest one to start with. That's okay. Let's just try putting a 2 here, and let's see what happens. So if we do that, that's going to give us now 2 sodiums. It's also going to give us, let's see, we now have 4 total hydrogens, and we have 2 total waters, or 2 total oxygens. So then we need to look at what did that do to the other side. Let's see here. So if I put a 2 in front of that, what does that do? That's going to give us 4 hydrogens and 2 oxygens. And we're most of the way home then. The only thing left I have to do is put a 2 in front of that sodium, and that should be balanced. Yep. Okay, so there's my balanced equation. Now, as far as ratio goes, okay, I'm going to start writing some of these at the top so I have enough space for it. I could have 2 moles of Na for every 2 moles of H2O, right? Or I could flip that. 2 moles of H2O for every 2 moles of Na. Okay? I could have 2 moles of Na for every 2 moles of NaOH. Okay, or flipping that, 2 moles of NaOH for every 2 moles of Na. I could do it then between the sodium and the hydrogen. For every 2 moles of sodium you use, you make 1 mole of hydrogen gas. Or if we flip that, right, 1 mole of H2 gets produced for every 2 moles of sodium that we use up. We could put it in terms of water and the sodium hydroxide. So for every 2 moles of H2O, we make 2 moles of NaOH. Or if you want to look at it, 2 moles of NaOH gets produced for every 2 moles of water. All right. We've got a couple more here. We could look at it in terms of water and hydrogen. So for every 2 moles of H2O, we make 1 mole of H2. Or for every 1 mole of H2 made, we had to use up 2 moles of water. And then the last one, the sodium hydroxide and the hydrogen. So for every 2 moles of NaOH, okay, we get 1 mole of H2. Or for every 1 mole of H2, we get 2 moles of NaOH. So it's a lot of possible, right, mole ratios here based on the balanced equation. Okay, now which one you're going to use depends on what unit you're trying to cancel, right? That's what we did that section back in Unit 1 is we picked out which ratio we needed to cancel something. So all we're going to be doing is trying to cancel units and pick, okay, whichever one of these things is actually going to cancel the units that we are in, all right? So that's what we are going to be doing here in the next section.